In section 4.9, we're going to be looking at the oxidation numbers of elements. This is very similar to in regular chemistry when we determine the charge of an element, but we have to take into account the electronegativity of the element to determine who will have the negative charge in the relationship. So first of all, here's the periodic table to remind us of the trends for electronegativity. As we go from left to right, electronegativity increases, and as we go from the bottom to the top, it increases. Fluorine has the strongest electronegativity. Here it's a little easier to see now. You see fluorine has a 4, and that's the highest value on the scale. The noble gases have very little electronegativity. At the bottom they start to, but we don't really need to worry about that. But as we go from left to right, it increases to fluorine, and top to bottom it increases. The only major exception that we deal with on a regular basis is hydrogen, and I need you all to remember that hydrogen is the same value as phosphorus. So if we had a bond between phosphorus and hydrogen, that would be a nonpolar bond because they have the same electronegativity. So let's look at some of the oxidation numbers that have already been assigned. In the compound calcium with 2 fluorines, calcium would have the +2 charge. It is much weaker than fluorine electronegativity-wise, so it will always take a positive charge. If fluorine, being much stronger, would always take the negative charge. So calcium has a +2 charge because it's losing 2 electrons to the fluorines, and each fluorine only gains 1. Between carbon and hydrogen, since carbon's a little bit weaker than hydrogen, sorry, I misspoke there. Since carbon's a little bit stronger, a little bit more electronegative, it's going to have the negative charge in this relationship. And it appears that carbon would have a -3 oxidation state, and hydrogen in this compound would have a +1 hydrogen oxidation state. Water also easy to break apart. Hydrogen's weaker than oxygen. Hydrogen's a 2.1. Oxygen's a 3.5 on this scale. So oxygen would take the negative value. Hydrogen would take the positive value. And then between iodine and chlorine, iodine is stronger, so it's going to take iodine is weaker, so it's going to take the positive charge, and chlorine is stronger, so it's got the negative charge. So I have assigned chlorine the -1 charge, or -1 oxidation state, and iodine has the +5 oxidation state. Now this one's a little more difficult because we have a polyatomic ion. First assign the common oxidation states, and then we'll work out what to do with that manganese. Oxygen's always a -2. So let's write a -2 oxidation state for oxygen. And the potassium is a +1, so we give that a +1. Well, the manganese is going to make up the difference so that this ionic compound is neutral. Now, with 4 oxygens, with those 4 oxygens there, we need to realize that it's a -2 charge for each oxygen, but since there's actually 4 oxygens, all 4 of them combine together to a -8. So in order to have the combined charge of the potassium, the manganese, and the oxygen together to equal 0, we can see that the manganese needs to be an oxidation value of +7. So potassium's a +1, the oxygen's a -2, and there's 4 of them, so the manganese has to be a +7. Let's do the same thing to the sulfate. So with the sulfate, I've got sulfur down as a +6, but let's kind of dissect it in reverse here. We have SO4 -2 charge. So the first thing I want to attack was the oxygen. There's 4 oxygens, and oxygen has a standard oxidation state of -2. So they combine together to -8. I don't know sulfur, but sulfur plus the -8 from all the oxygens equals the polyatomic charge of a -2. This is a major difference here. The polyatomic ion is not neutral. Polyatomic ion is a -2. So this is not going to add up to 0 like it did in the KMnO4. It's going to be X plus -8 equals -2. That means that the sulfur has to be 6. So the sulfur is a +6. +6 and -2 is -8. This is a skill we're going to be doing off and on for the rest of the chapter. We're going to have equations like this one, and you have to pull it back apart and try to figure out, okay, what's the iron's oxidation state? What's the oxygen's? Now, aluminum here is in its standard state, so it's a charge or oxidation state of 0. And now, at the end of this reaction, iron's an oxidation state of 0. And let's look at several more reactions. Here we have oxygen in its standard state as hydrogen and oxygen are both in their standard states as gases. And anytime an element is pure and in its standard state, its oxidation value is always 0, because that's its standard state. But then it's reacted and formed water. Well, oxygen's a -2, so the hydrogen must be a +1. Here we have solid zinc. That's the standard state for zinc, to be in a solid when it's all by itself. So we say its oxidation state is 0. Copper's a +2 when it's aqueous here. So that means its oxidation state is 2. And so forth and so on. I've dissected each one of these polyatomic ions or molecules to figure out each individual element's oxidation state. Now we need to know this so that we could figure out what's happening to each element. So we could see in this one, here, hydrogen was a +1. The reaction takes place, and hydrogen's still a +1. So it didn't gain or lose any electrons during the reaction. It's now bonded to oxygen, but the hydrogen didn't gain or lose any electrons. The oxygen went from a -2 charge, and here it's a -2, and there it's still a -2, so nothing happened to the oxygen. But the manganese, here we have manganese as a +7. When the reaction's over, we have it as a +2. So if this manganese is going from +7 to +2, it must be gaining electrons. And to go from 5 to 2, it has to gain a -5 charge. That would be 5 electrons. It's gaining 5 electrons in the reaction. The carbon is the other thing that's changing. Carbon here is a +3, but on the product side it's a +4. So its charge is going down to +4. That means it's losing an electron. Now, chemists have assigned names to this idea of something gaining electrons, as manganese did, something losing electrons like carbon did. They say if something loses electrons, then it's oxidized. So lose electrons is oxidation. Now, if it gains electrons, we call that reduction. Its charge is being reduced by gaining electrons. And the little phrase we usually say is LEO-GER. So lose electrons, oxidation, gain electrons, reduction. So this hydrogen is going from a 0 charge to a +1. So it lost an electron. It has been oxidized. Whereas the oxygen here went from a 0 to a -2. If it's gaining electrons, that's called reduction. So we went through each of these equations to figure out first what their oxidation state was, and then whether or not it was gaining electrons and being reduced, or losing electrons and being oxidized. And then some of them were neither oxidized nor reduced because their charge didn't change, like the chlorine in C here. Chlorine's a -1, And when it's all said and done, it's still a -1, so it's neither oxidation nor reduction.